Hello guys, we are back with our next lecture. In this lecture, let us go through the heap sort algorithm. So how computer will be doing it. So we did in the last lecture, right? So we did with the R method. So basically that is the exact method. If you convert that exact method into code, you will be getting the computer method. So that's what, right? Okay. So now let us go through how a computer does the heap sort. So I'll be explaining you parallelly with an example, guys. So please concentrate. If possible, take a piece of paper and just write down the steps how I am explaining you and how the algorithm is running, so that it will be 100% clear for you. Okay. So heap sort. Initially, this is the whole algorithm, guys. Heap sort. Okay. So heap sort is of A. So basically, A is nothing but the array that for which we want to do heap sort. Okay. So the first and foremost step is nothing but a build max heap. So first of all, you need to build the max heap for it. That's it. There's nothing more than that. Okay. So once you see this, let us move on to that. What is max heap? Building max heap. So I think everyone saw the last lecture in which we discussed for this example. Okay. So if you want me to open the exact paper which we discussed, that will be better for you, I think so. Okay. So this was the given example and we built a small heap for it and we found the max heap for it also. Okay. So let us do it with the help of algorithm now. Okay. So once you started max heap with an array, you went to build max heap. Okay. We came here. So this is nothing but built max heap. So I have just given numberings, guys, so that you can just observe it clearly. Okay. So 1. So here the first step is nothing but heap underscore size of A is equals to length of A. So basically heap size is nothing but a number of elements inside a heap. So how many elements will be inside a heap? So the number of elements inside a heap is nothing but the number of elements in an array, right? That's a simple logic. So if in array we are having 7 elements, in heap also we'll be having 7 elements. That's it. So that is the reason why I'm just initializing the length of heap is equals to 7. So there is a major reason for doing that. You will be understanding now. Okay. So assume that, I hope everyone remembers the flow how we will be filling the tree. So here will be the first element, second, third, fourth, fifth, sixth, seventh, eighth, ninth, and so on. Like that it will be continuing below also. Okay. So assume that the maximum elements in which we have given the example is 7, right? So till 7. Okay. So now we need to do the operations like checking and swapping. Okay. So let me revise the concept once again so that will be clear for you. So once you drawn the heap, this is a normal heap. This is not a max heap nor a min heap. To convert this into a max heap, you will be checking whether whether it is having children. If there are no children, you will be just skipping the step. If there are children, you will be comparing the parent with one children and finding the maximum value and the maximum value with the another children and finding the total maximum value among the three, and you will be storing the maximum at the parent and you will be swapping with that particular thing. So if you assume here 40 is the maximum but 5 is the parent, so you will be swapping 40 and 5 in that way. Okay. So if there are no children, you should not do the process, right? Okay. So how you will be identifying whether there are no children? So for that we will be using this thing, guys. So for of I is equals to, this is nothing but equal to, guys, in pseudocode we will be using these kind of symbols, length of A by 2. So length of A is 7 by 2 with the lower bound, remember that. So if you assume we are having only 7 nodes or 7 elements in an array, 7 by 2, that is nothing but 3.5. So that is nothing but lower bound will be 3, right? Okay. So for 1, 2 and 3 you need to do the operation. Okay. Similarly, if 8 is included, so 8 by 2, that is nothing but 4. So till 4 you need to do the operation. As it is indirectly having the children. So this is a small trick to identify whether it is having the children or not, because we are following the left to right. So only, okay, if you want, You can even consider this as the total length because there is nothing to lose, right? There will be no swapping up occurring there. So instead of removing that confusion, we will be doing it in this way. So length of a by 2. So this thing is to identify the elements which are having the children. So it will be selecting only this if there are 8 or 9 elements. So if there is a 10th element, it will be coming to this side also. 11th, 12th element, it will be coming again like that. So based on the length, it will be identifying how many elements will have children. Okay, because each element will be having 2 children, we'll be dividing it by 2. You can even remember in that way. So down to 1. So you'll be coming from bottom to up. If you remember, I have just drawn the diagrams also for these things. So you'll be following down to up process. So that is the reason why you'll be doing from maximum to minimum movement. Okay, so in each step you will be doing the maxify of a comma 1. So maxify is a process where you will be searching the maximum element and putting it in the corresponding parent. So if you take these 3, you will be placing the parent here. If you take these 3, the parent here. If you take these 3, the parent here. In that way, placing the parent in the exact position. Okay, so do max heapify a comma I. Okay, so after that we are having the heapify. This is the last part of the algorithm. Okay, so max heapify a of I. So initially you will be considering the leftmost children. So if this is the parent, then we need to find the left and rightmost children, right, to calculate their cost or their weights inside them. Okay, so you will be getting those values directly from L of left I. Left I you can directly write in this way, or you can write it 2I and 2I plus 1. Okay, so if you just observe a small logic here, I'm just taking a rough paper. Okay, so here if you observe 1, 2, 3, 4, 5, 6, 7. Okay, so if you observe here, this is dividing into 2, right? So if it is 1, the children will be 2 into this and into, so 2 into 1 plus 1. Similarly, this equal to this into 1. Sorry, this into this, right? So 2 into 2 plus 2 into 2 plus 1. So that is nothing but 2 into I plus 1 and 2 into I. So this will be the left children, this will be the right children. Let me explain again, so that will be clear for you. 2, 3, 4, 5. So if you want to identify the children of 2, the left children will be 2 into I. I is nothing but the number. So 2 into 2 equal to 4. 4 will be the left children. So just add plus 1 for this to get the rightmost children. Plus 1, 5. So that is what is used here to identify the left element and the right element. So I will be identifying them and storing in left and right. Okay, it's clear, right? Okay. So after that, I told you we will be comparing the left element with the right element. Sorry, left element with the parent and the maximum element with the right children. So that is what I have just written here. So if left children is less than or equal to heap size of A and A of L is greater than A of J. So this is what? The left children is greater than A of J, A of I. I is nothing but the parent, right? Okay. So if it is true, we will be doing the largest. So I have defined a variable largest. So in that I am storing the value of L. So the new value I'll be storing in L. If not, I'll be continuing with the largest indices as I only. There is no change. Okay. So after that, if, so this is done. So the next step, you'll be comparing with the rightmost children also, right? Okay. So if R is less than or equal to heap size of A. So basically we are again checking whether that element exists or not. Okay. And A of R is greater than A of length, A of largest. So the maximum element is again compared here. So if it is true, now the largest element will be the right side element. So that right element index will be stored in the largest. So finally somehow we will be managing to store the largest element index in the largest among those 3 elements, like the 3 triangle elements. So if the largest element is not equal to I, so that is indirectly saying that there is some change in it. So in that situation, we will be exchanging A of I with A of largest. So this exchange, assume that that's a small function to swap 2 elements. That's it. Okay. So after that, you will be doing max heapify A comma largest. You'll be understanding it why again I am doing this. Because yesterday, like in the previous lecture, if you recall it, in one case, even after heapifying it, so if you assume here, Okay, so this is in between, guys, so don't get confused. Let me check it where it is exactly. I think it is here only, right? 25 with it. Okay, I'll be just showing it in the book while we are discussing example. So this is nothing but max heapify. So after that, you'll be continuing the process until you will be completing the whole graph max heapify. So this continues until the whole graph. Okay, and after that we'll be coming to this. So this is nothing but where you will be considering the heap sort, the basic heap sort. Like I told you, right? We'll be deleting the topmost element. Like by swapping with the last element, we'll be deleting the topmost element, and you'll be again doing the heapify. So for of I to length down to 2 until 2, because at last you'll be left out with one element, and that will directly be pushed into the stack. Sorry, pushed into the array, you can say. Okay, so the first thing that you will be doing is do exchange of first element, that is nothing but root, with the last element a of I. So heap size of a is equals to heap size of a minus 1. I told you we'll be deleting the last element, assume that it's not there. So that is what minus 1 indicates. So once it is done, you'll be doing again heapify, because it will not be a max heap once you delete a particular element. So that is the reason why you'll be doing a max heapify, and this process continues. So I think you got some clear idea, some basic idea at least. Okay, so once we are going through the problem, you'll be getting a clear idea. I'm sure about that. Okay, so the first thing that will be given in this situation will be the array. So you'll be starting with heap sort. You'll be building the heap. So building heap is nothing but you'll be assuming it in this way. Like basically remember that the computer will store any kind of data in terms of array representation only. There is no concept of graphs or anything storage inside a system. So just for human understanding and faster understanding, we converted them into trees for easy understanding. Okay. So 20, 35, 10, 25, 40, 8. So all these are stored here like this: 20, 35, 4, 25, 48. So this is just a representation. So I have just written clearly just a representation of a fast understanding. That's it. Okay. So now in step 2 here, in the array I told I will be doing the length by 2. So here length, the lower bound of length by 2 is 7 by 2, that is 3.5, that is 3. So you need to do the process at 3, 2 and 1. So why I wrote from 3 to 1? Because it is in reverse order. If you remember, down to 1. So it is down from maximum to minimum. So 3 to 1. So the operations that you should do at 3 and at 2 at 1 are defined here. So basically inside what you should do the max heapify. So max heapify, okay. So max heapify is nothing but you'll be comparing the, I have just written here, indices of the left and right children are substituted, checking whether the left and root which is max. So you'll be storing the max in the largest. Similarly checking right and max which is the maximum. Swap if needed. That's it. So these are the 4 steps which you will be following in it. Okay. So first thing you will be checking with, I have just written it here guys clearly. So at 3, first you will be checking 40 is greater than 5 or not. It is true. So you will be swapping max equal to 40. So assume that the largest does not store 40. Largest stores the index of it, guys. So 40th index is 6. So largest stores 6. Okay. So I didn't write anything about largest because that will be a bit complex and confusing to understand with both of them. So I have just written with respect to numbers. So again, next you will be considering with this, right? So 40 is less than 8, which is false. So maximum is equals to 40. So you will be swapping it. Okay. So once it is swapped, you will be getting the result. Okay. So again for next step is nothing but at a 2. So now here it is 40 guys. Please update it or update in the array. So that will be 100% clear. At 2 here we are having 30, 10 and 25, right? Okay. So 30, 10 and 25. So if you observe here, already 30 is the maximum. We know it, but computer cannot know it. Computer will blindly follow the steps that you give. Initially it compares these two. Maximum is 30. So in max, still it is having the value 30 and in largest it is having 2. Again comparing these two, 30 will be the maximum. So there is no swap done here. At 1, so I updated the graph here. So at 1, this will be the graph 20, 30, 40, 10, 25, 5, 8. Okay. So if you observe here, so you will not consider these things. So 20, 30, 40. So these two compare, you'll be getting 30 as the maximum. When you compare the maximum with 40, you'll be getting 40 as the output. So basically at the end you will be swapping it, and 40 will be the parent, sorry, 40, 30, 20, 10, 25, 5, 8. So this is the result of max heap. Okay, so this is a process which will be continuing after every step, guys. Whenever the computer thinks that there is a chance of losing the property, then it will be checking it. So now we'll be continuing with the heap sort. So basically now we are done with only a single step in the main heap sort. Now we will be continuing with the deletion process, that is nothing but heap sort, the main process. Okay, so heap sort, if you observe here, the length of the loop is from I length down to 2. So from n to 2. Sorry, from n. Just give me a second, guys. Okay, so let us continue. From 7 to 2. 7, 6, 5, 4, 3, 2, 1. So there are totally 7 operations that you should do. I have just written them one after the other so that will be 100% clear for you. Okay, so initially if you recall the steps, initially we'll be exchanging it, you'll be deleting the last element, and you'll be heapifying again. Okay, so I'll not be repeating backward again with the algorithm, I'll be just explaining you here. So firstly you will be swapping the 7th element with the first element. So here I have swapped it 40 with 8. Okay, so after that you will be comparing 8 with its children. You will not be considering these things. Okay, or you can do from bottom. So better do from bottom, guys, that will be better. Okay, so 30, 25, 25. So here is there anything to change? No. Here is there anything to change? No. Here is there anything to change? Yes. 30 is the maximum, so push 30 to the top. 38, 20, 10, 25, 5, 40. 40 is not there, so that's the reason why I have just indicated with dotted line. So if you recall it, I told you here we need to do again max heapify if you do anything, any changes, right? So why I told you that, if I consider this, from here I gave 3, 2, 1. So all heapify process is done. But after heapify also, I got a situation where there is still an issue. Here there should be 25, not 8. So that is the reason why if you change something, you need to do heapify. That's it. That's the only solution to resolve that issue. Okay, so again I'll be doing heapify from here. At the third position, no change. Second position, the 25 will be coming up. And first position, no change. So finally you'll be ending up with this result. Okay, so at 6. So I'll be doing it a bit fast now. So I swapped the last with the first. 30. Here we'll be swapping these two. So here there is no change. Here there is no change. Swapped. Again we got an issue after swapping also. So again we'll be swapping with the maximum. So we got this as the result. So again you'll be swapping this with 8. So 8 here, this is gone. This element has been deleted. These elements have been deleted. So in this, the maximum among this, there is no need to check here. So we'll be checking from here. It's already following the max heapify property, max heap property. You'll be continuing here. At here it should be 20. So you'll be swapping these two. So you'll be getting this as the result. Again you will be swapping 20 with 5. So you'll be getting this as the result. Again after an observation, you can swap. You need to swap these two. You'll be swapping them. So you'll be getting these two. Again you'll be swapping these two to delete. So you'll be deleting the 10 finally from there. And you'll be getting 5. So at the end you'll be getting 2. At this end you'll be getting only 5 as the root, that's it. So 5 is the minimum value, and if you represent it in a reverse order you'll be getting in this way. If you store them in the order it went outside, so that order is nothing but the descending order, or you can even reverse it and make it as ascending order. 5, 8, 10, 20, 25, 30, 40. So in this way the heap sort works, guys. So I hope everyone got a clear idea on this heap sort. So if you ask what time complexity will it take for this algorithm, it is nothing but n log n to sort. So your question will be, so how did I say that it will take n log n of time? Okay. So the answer for that question is really simple, guys. So basically here you are constructing, here you are building a graph, right? So basically building a graph is nothing but you are just arranging them in this way. Like internally they are not arranged, but we will be assuming them as they are arranged, right? Okay. So if you observe here, this loop, so this loop continues how many times, guys? Log n times. If you remember, we have discussed how I told log n. So basically it is dividing by 2. So it is again becoming 16 will become 8, 8 will become 4, 4 will become 2. So this is nothing but logarithmic decreasing, right, in terms of log. Okay, whereas this loop continues till the length. I'll be just assuming this as 1 only, so it's 1 is very neglectable, right? So 1 and n, sorry, 1 and 0, 0 and 1 are not neglectable, the values, when compared with 1000 or 10,000, right? Okay, so similarly I'll be assuming that as this operation takes n times, so this both will take n log n, and these all statements are just if conditions are normal conditions, right? So there is no need to consider anything, all take 1 unit of time. So the only thing that we will be considering in time complexity are loops. Remember that, while loop, do while, if will not be considered, for loops. Okay, so here this for takes n and this for takes log n. So as this loop is inside this, this will take n log n time. That's it. So that's the simple logic to do it. Even I heard that there are some derivations for it. If you want, you can go through them, or you can follow it in my way of trick. Okay, so I hope everyone got a clear idea on this. So in the next lecture we'll be introducing about hashing. Thank you, thanks for watching.